After a whirlwind demo at CES 2025, Alex is back in business to take a look at the very first game with a shipping RTX Mega Geometry implementation, Remedy's Alan Wake 2. Now this promises to bring some of the performance enhancements that enabled the stunning Mega Geometry demos that we saw at CES to a game that already packs some pretty considerable geometric detail. So Alex, are you ready to walk us through RTX Mega Geometry in Alan Wake 2 today?
That's why I'm here, and it's the only thing I do.
Okay, Alex. So what is RTX Mega Geometry? Can you break it down for us, and can you explain exactly what it does and what it could mean for games?
Yeah, so RTX Mega Geometry is essentially a rather large change up to the ray tracing API. So in the past, games have used DXR or Vulkan ray tracing, which used a very similar system, actually. And ray tracing, one part of it is shooting out rays, of course, and seeing if they hit stuff. And another part of it is building this structure called a BVH, an acceleration structure that contains the geometry and all the game doodads that is then traced against. And this building part of it, it's all actually done on the GPU in the PC space. There are commands that have to be processed by the CPU to allow this to occur, because there's always kind of this syncing between CPU and GPU. But all the building is done for this acceleration structure is done on the GPU, and RTX Mega Geometry actually kind of wants to make more of that to be a GPU-driven process. And also it's trying to change up kind of the granularity at which this BVH building occurs. So in the past, there would be a top level and a bottom level BVH, and in all these little bottom level BVHs, there'd be the groupings of triangles. And that was pretty good for a time when there was a lot more static geometry and worlds were smaller, and maybe there was less geometry overall. But nowadays, modern games have a lot more geometry. They can potentially have a lot more moving and deforming geometry. Or in the case of games that use mesh shading or things like Unreal Engine 5's Nanite, there could be a bunch of triangles that are being added to the frame every single time the camera moves, because there's really good level of detail systems, or there's continuous LOD systems like we see in Unreal Engine 5. And that makes it extremely expensive to process and make this BVH on the GPU. And of course, there's that command cost on the CPU. So this is an API change primarily, and it targets actually all RTX GPUs since RTX 2000. And this goes above and beyond what DXR does. So what we're seeing here, presumably in Alan Wake 2, is using, I would presume, NV API, but there's also Vulkan extensions right now that are specific to NVIDIA. That's the way Vulkan works. We'll talk about this at the end of the video, but this may be a glimpse of what is to come actually for DXR. So yeah, as I mentioned earlier, there's this bottom level and top level structure to a BVH in DXR and Vulkan ray tracing. And actually, I'm pretty sure it's the same on the console side of things. And here, the difference with RTX Mega Geometry, the one that I'm going to be specifically talking about in this video, is the addition of the CLAS, the cluster acceleration structure. There's the bottom level, the top level, and now there's this cluster level in the middle here. And this maps very well essentially to games that use mesh shading and games or something like Nanite, where triangles are grouped into clusters and then traced against separately, kind of. And this is an interesting trade-off because it shouldn't just be taken as a pure advancement over what was previously available as part of the state of art, this bottom level and top level. This CLAS structure is one, it's better for games that use stuff like mesh shading, but it's also just a generally perhaps better thing to use for stuff that moves, stuff that deforms, stuff that levels of detail changes rather often, or things that procedurally add more geometry to the scene, like tessellation, real-time tessellation. And those things previously in the past were way too expensive to potentially do constantly changing stuff like that in real time en masse. And the this cluster acceleration structure is a way to solve that is not GPU specific at all. There were other attempts at this before, research in the past, but that all required stuff that might have required larger changes to hardware and GPUs. And here, this is more of an API change. So it really does actually support all RTX GPUs. And I imagine it would easily support stuff like AMD and Intel GPUs, actually. So that's really cool. And in Alan Wake 2's case, the reason why it is in this game at all, and the reason why it's a big deal for Alan Wake 2 is because specifically in all the areas of the game that have a lot of vegetation, Alan Wake 2 very specifically uses skinned geometry. That means geometry where the actual vertex positions change each frame on the geometric model itself. They don't use like some sort of tricks like a lot of other games do to fake vegetation movement on the geometry. And as a result, it's pretty expensive to ray trace against. It's accurate, but it's more expensive to ray trace against using the traditional way this is done. And RTX Mega Geometry here is trying to kind of make that cheaper either on the CPU, in VRAM, and also on the GPU. So here I actually did measure that depending upon what GPU you have, there's going to be differences in how much RTX Mega Geometry can potentially improve performance. Now I went through this really cool benchmark that we have as set up by our internal tools as made by us and Illusion. And running through the benchmark on the RTX 2080 Ti, I saw at 1080p here, and this is 1080p native, by the way, really low frame rates, but I saw a 13% higher average frame rate there on the RTX 2080 Ti. Now, that doesn't seem like much, but this Turing GPU is running 8.4 milliseconds faster in the new version here in this really intensive GPU scene. That's half of the frame time for a 60 FPS frame rate. So it is shaving off a whole ton of GPU time here for this GPU. What that means practically on a GPU like this is when playing the game at DLSS quality mode, as we're seeing here, we can see that it was previously in the mid-20s before primarily, but now it is almost always north of 30 FPS. And this is with direct lighting on, as well as the low quality for the path tracing implementation. So that makes it so that an RTX 2080 Ti couldn't play it before, but now it actually has what I would consider controller-friendly frame rates. So it's basically making path tracing work well on an RTX 2080 Ti, which is a big deal. RTX 3080, going through the benchmark again, here I saw on Ampere, presumably just due to the metrics being different, less of an impact. It was only around 10% higher average frame rate. Still, once again, really low frame rates here at native 1080p, because native 1080p path tracing is really expensive. And that was around an average 3.5 milliseconds faster in the benchmark scene. In game, though, less impressive at like a realistic resolution that you'd use here. Once again, 1080p quality mode. Running through the forest, I saw where it wasn't before, sometimes going down to the 30s. Now it was primarily always above 40 FPS. It just made it presumably a better experience if you wanted to target something like, 40 FPS while playing this game. Now, when you get to RTX 4000 and 5000, this is where things get less exciting and interesting, and I'm not exactly sure why. Just doing the bench, for example, for RTX 4090, it scored only something like less than 1% higher average frame rate over the course of the bench, and that was run multiple times. You would really struggle to see a difference. Technically, there's now obviously, less of a CPU burden, so there's potentially higher frame rates on that end, and there's less VRAM usage, but on an RTX 4090 at 1080p here, I didn't see almost any difference. I also ran it on Blackwell, RTX 5080, and they've touted that Blackwell's the best at RTX Mega Geometry. Here, I, once again, at 1080p saw less than 1% higher average frame rate improvement there by using Mega Geometry on the RTX 5080. And when I went up in resolution to like 1440p and 4K, I actually, over multiple runs, rerunning it multiple times, saw technically a tiny bit less performance with RTX Mega Geometry, something like, like half of a percentage. And you can sometimes see that playing out in the average frame rate counter there. So for some reason on RTX 4000 and 5000, as far as I can measure in the scene I've used here in the forest, where I would presume it would be the most impactful due to all that skin geometry, Well, I haven't actually seen that big of a difference here, and maybe potentially a little bit less performance. Maybe this has to do with drivers or the implementation at the moment, but right now, the people that benefit the most from this on the GPU side of things are those that have Turing and Ampere cards.